Hi, it's 10 a.m. I'm Arlie Montalvo from the Riverside San Bernardino chapter of CMPS. I'm not Nick Barth, like it says on the screen. He will be coming up later. But I do have just a few announcements to make. I just would like to thank all the amazing volunteers. There are like over 40 that helped with our California Native Plant Society native plant sale last weekend here at the RCRCD, where we offered plants appropriate for the Inland Empire. We were able to raise, profit about almost, 5.5K, which is really nice because that's sufficient to support our programs and also to make donations to appropriate conservation causes and organizations, and to support scholarships for students for various activities. So it's really wonderful. So just thank you, everybody, for helping us do such a successful sale. It was a lot of hard work. But now we have another opportunity, okay, next weekend in Rancho Mirage on the Saturday, November 22nd, is the plant sale that focuses on desert plants that are appropriate for the desert region. And so Katie Barrows is in charge of that. You can go to the website to see the flyer. And I think there will also be a list posted of a list of the plants that will be available. And possibly there's just a few seed species as well. And I think Katie is putting the link to the website in the Zoom chat. But I also put our Riverside-San Bernardino.cmps.org website right here. You can go on there, click on Buy Native Plants, and then under that, you'll see the two plant sales. You scroll down and you'll see the desert plant sale flyer, and then there will be something to click on if there's a plant list to see. So that's great. And thank you, Katie, for organizing that. You and Kevin have done an amazing job there. There will be volunteers helping them set up on the Friday before the sale. And boy, the rain is really pouring now, which is kind of nice. One thing about the rain is that maybe we will have plants up in February, and one of our programs that's coming up in February, the third Saturday of February, is identification of weed species that Chris McDonald will be giving. So last year it was too dry, and so we did a different talk. I think we may have it this year. So the other thing I wanted to mention is our December program is going to be December 20th. It's going to be here at the Resource Conservation District, but it will be in Building F, where there is a kitchen, because we will have our annual sort of social, slideshow where people contribute their favorite slides they took through the year, and a potluck. And so be prepared for that. And I think we will be selling leftover seeds and bulbs at that as well at a discount. So come and enjoy that. And then the fourth thing I want to mention is that our CMPS conference for 2026 is coming up in February. So it's going to be a great conference. The program is now available on the website, so you'll be able to see what the different program slots are, on the 5th through the 7th. There are also some workshops and field trips available, not that you can register for separately the day before the symposium begins. And there are scholarships available for that. You need to go to the conference website to see that. If you're low income, underrepresented people of various kinds, students, early professionals that really can't afford to pay the conference fee, there are special discounts for certain levels. And then there are some scholarships available to help defer the cost of the registration and fee, travel fees. And so if you click the registration button, you'll be able to see a line for scholarships, and click on that and explore it. I do encourage people those applications are due by November 30th for scholarships. The other thing I would like to mention, I'll say first, is that the Resource Conservation District, where we purchased most of the plants that we sold at our plant sale last Saturday, is now open for business. Okay, they have a great selection of native plants, seeds and bulbs, and they will be open for business here at their little kiosk through spring until sometime in early spring. And so you can come here for plants, and then also I stopped by Parkview Nursery in Riverside, the one on Chicago, the other day, and they have a really nice selection of California native plants that are appropriate for this region. So do visit the local nurseries, yeah, and support their continual their ability to provide and sell native plants for your gardens. It's really great. They looked really healthy as well. And then also, as I mentioned last time, it would be really great if we can find somebody to coordinate a t-shirt contest, a t-shirt design contest. And I'm going to show you again. Last time I showed you what the San Gabriel Mountains chapter did. I'm going to just pull this up, and you can see that this is a t-shirt that the North Coast chapter did. And you know, these t-shirts are really beautiful. Lots of chapters have designed t-shirts that sell well. And I don't know that we can get this done in time for the conference, but it sure would be nice, wouldn't it? And then that's any other announcements that I've missed that anybody has? So I think we're okay. So what I like to do is introduce our speaker for today. We have Dr. Nicolas Barth from UC Riverside. He's in geology an associate professor. And you will sometimes see a paraglider coming down off of the box springs. It's probably him, okay? Or running on the trails way out, you know, who knows where, or climbing rocks. And Nick has a really great background in geology. He did his first degree at UC Santa Barbara. He was probably surfing, you know, quite a bit of the time at that, yeah. And then he went off to New Zealand to do his PhD, and he still has research that he does, geological research in New Zealand. And I'm just going to hand it over to him. Enough of me. So thank you, Nick.
Great, thanks. Okay, thanks everybody for braving the rain to be here, and thanks to those of you joining from Zoom. I'll dive right into it. So I suspect this is probably a little bit of a different talk than you typically get, but hopefully you find some things that are interesting and come away with a little bit of a different perspective on California native plants and California's really amazing biodiversity more generally. And so I wanted to start with this drone photo I took in 2023, kind of lower part of the Carrizo Plain area. And you can see there's some very nice sequence of folded sedimentary layers. You can see the layers through here, and they're folded across this terrain. Kind of annoyingly, there's some soil and plants covering the beautiful rocks here. But I show this, I think it's a really nice illustrative example where you can see in this one view with this one area, the distribution of plants is not random, but there's some order to it. It has quite a lot to do with the rock types that are underneath. And so you can see some of these purple flowers here are choosing some of the layers in the rock over others. So there's some bare spots that they don't like those layers, but they're happy to grow on others. You can see there's some drainage. So there's kind of these little mini gullies that also are good growing conditions, getting a little bit more water. And you can see there's different slopes. So there's some slopes that have more soil on them. They're facing specific directions, giving plants a better amount of sunlight. So there's a lot of variation that's happening here on a local scale. And so I'm going to kind of try and, throughout the talk, illustrate this on a California scale. And then on the right here is a cartoon I quite like of California in a blender, and you can see these very geologic buttons, and we'll, in short order, talk about those different buttons that help build California as we know it today. And so this is the overview for my talk. So we're going to go through plenty of geology backgrounds, give everybody a crash course. We'll talk about geologic time, which is quite different than human time and hard for us to wrap our heads around. We'll go into a brief history of life, and I'll give you a brief overview of plate tectonics. And so with that, that'll take us into talking about how we assembled California as we know it today. And then we'll go through different demographics related to the state, and then a few case studies towards the end, including a shift more towards the Riverside region as we go through it. So I'll start with this. This is a geologic timeline here. So on the left side, we have basically the start of the Earth, birth of the Earth. And on the right, we have present. And so this is to scale, showing some of the major milestones through the course of Earth's history. Text is probably a little bit small to read. You don't have to worry about the details. But we start at about 4.6 billion years on this side, and then work our way up to present. And so for humans that we really just, if we're lucky, we see 100 years, it's really very difficult for us to think in terms of thousands of years, millions of years, billions of years. So really difficult to kind of wrap your head around this. And one kind of slight trick I have that helps a little bit, so I use this with students, is if you think of all of geologic time as one roll of toilet paper. So an average roll of toilet paper is about 230 sheets. And so each sheet that you tear off is about 20 million years. And so if we think about a roll of toilet paper and unravel that through time, we can then think about these milestones in a slightly different way. And so 4,600 million years ago, 4.6 million years, is the age of chondrite meteorites. And these are like some of the most raw kind of materials that are left over in our solar system. So this is our good approximation for the age of the Earth. So about 4.6 billion years. So that's where our toilet paper roll starts. The oldest mineral grains are about 4.4 billion years. And so that's five sheets in is the oldest piece of Earth that hasn't been recycled yet. Okay. And then we go quite a bit further in, 40 sheets in, and this is the oldest preserved sedimentary rock. And so because we have plate tectonics, it's really effective at recycling materials. And so the oldest preserved sedimentary rocks that we have at the Earth's surface are 40 sheets into this 230 sheet roll. The first fossil evidence of life, that's about 55 sheets in. And so this is primitive bacteria. And then we can actually skip forward quite a bit. So if you imagine a cat, unwinding all the toilet paper roll, we're going to skip more towards the end of the roll. And so now we're 30 sheets from the end of the roll. And this is where we have an atmosphere that's more similar to our modern atmosphere. So we have oxygenated atmosphere, and multicellular life is really kind of starting to kick off about 600 million years ago, or 30 sheets from the end of this roll. The first mammals and dinosaurs are 11 sheets from the end. The dinosaurs end about 3¼ sheets from the end. And quite importantly, our species, Homo sapiens, modern humans, we are last 2 square centimeters. So not even a full sheet, we're 2 postage stamps worth of that toilet paper roll. Okay, so again, our whole history is very kind of very short. And so the next slide, I'm going to zoom in on this last piece where we really have this, the last 550 million years or so, where we had this evolutionary Big Bang, all this multicellular life, and lots of kind of innovation in life. And so here we are zooming into that. And so we have 540 million years on the left side here at the start of the Cambrian period, going up to present on the right side. And we divide time in various different categories. This Mesozoic one is kind of this period where the dinosaurs are. But key thing here is that we're dividing time up. We have appearance of different species, including ones that we no longer have. So things like ammonites and trilobites and weird armored fish and things like that, dinosaurs, of course. And then we have all these major mass extinctions that have been global in scale, where we've had a huge turnover of species and life kind of starting over again to some extent. And so I just wanted to highlight like one really incredible, again, to emphasize it, we're the last 200,000 years on this whole giant time scale. Horseshoe crab, really amazing, first appeared somewhere around 445 million years, and it's basically persisted to present almost completely unchanged. And so horseshoe crabs, you can still find them cruising around on beaches in Florida. And so they're a really incredible example of this creature that's been able to persist for half a billion years. Pretty incredible. Okay, so we'll talk a little bit more about plants. So these are some major plant milestones. And so these are the major groups of plants. So present is at the top, and then down at the bottom, we have about 500 million years ago. And so the oldest plant groups are algae and mosses. So those have been around the longest. About 400 to about 350 million years or so is when we start having ferns and horsetails appear. So kind of first seedless vascular plants, and also conifers. So those are kind of also fairly old in the scheme of plant innovations. Ginkgos and cycads kind of dip slightly into the Permian. So this is kind of just before the start of the dinosaurs, about 250 million years ago is when those different groups started appearing. And then the latest innovation in plants is really flowering plants. So angiosperms really kind of dip back about 130 million years ago. So you can probably imagine, the innovation involved in relying on other species to help pollinate you is something that took time to kind of get organized in our history of life. And so they're the latest innovation. Okay, so California, we have a very nice record of marine fossils. Terrestrial fossils are comparatively a lot rarer in California. So we do have some, and from those we can pull out some records of past California native plants. And so I'll go through a few examples starting from kind of more recent, and then we'll go further and further back in time. And so we know from the La Brea tar pits that up until about 13,000 years ago, we had Rocky Mountain juniper. So plants that like to be in the Rocky Mountains, we actually had in downtown Los Angeles about 13,000 years ago. There's a forest up in the Napa, a petrified forest up in the Napa area that's about 3.5 million years old. And in that forest, the fossils, they found extinct species of redwood that are distinct from the ones that we still have today. Species of alder, myrtle, tan oak, rhododendron, huckleberry, and the extinct oak. So there's quite a diverse forest in that particular area at the time. And then we can go a little bit further back in time. So in the Anza Borrego area, southeast corner of the state near the Salton Sea, we have fossils from an ancestral Colorado River delta there, where we had cottonwood, walnut, laurel, willow, ash, cabbage palm, and avocado was actually native at that time. We have fossil evidence of oaks being in Northern California since at least 16 million years ago. So they've been a fairly persistent species in Northern California. And just to kind of highlight that redwoods used to exist from Alaska to Pennsylvania until about 10 million years ago. So redwoods used to be much more widespread than they are at present. And really, they've kind of just found these little refugia in California to kind of persist in. And if we go really back a little bit further back in time, so about 55 to 65 million years ago, we had tropical and subtropical plants in the Mojave Desert. If we go back to 80 million years ago, we actually had cycads and ancestors of coffee and tomato plants in Orange County. And so, it depends a little bit on your perspective. If you're a geologist, you might think of California native plants in a little bit of a different way and count plant cycads in your gardens and things. So yeah. Okay, so we'll shift to talk a little bit about plate tectonics. And so this is a global map here, probably inverted from what you're used to usually seeing. And so on this, all the continents, everything above the surface of the ocean is blacked out. And what we're looking at is colors that are showing the depth of the oceans. And so plate tectonics, biology has had a number of major breakthroughs, evolution, understanding of genes, DNA, all those sort of things. Plate tectonics is kind of like the biggest breakthrough that Earth science has kind of had as a whole to be able to tie in a lot of observations that we have on Earth. So we notice patterns in earthquakes and volcanoes and where mountain ranges are, valleys, all those sorts of things. But it really wasn't until plate tectonics that we're able to kind of tie this all together. And so as I'm suggesting, the key really was the oceans. And so in World War II, we had a lot of military ships that were out towing sonar and also magnetometers to look for German submarines and also to figure out where to put our submarines. And so as a result of that, we learned a lot about the magnetic properties of the rocks underneath the ocean and also the topography, where there was ridges and low places and things like that. So you can see that the topography looks quite organized. There's places where these kind of long, very linear ridges. There's places next to some of the continents where we have very deep trenches. And so all of these were kind of a surprise until we started mapping the oceans. And so by the mid-60s, we had enough that we were really able to kind of understand what was going on underneath the oceans. And it wasn't really until like the 1980s that like plate tectonics was really well accepted by the majority of the scientific community. And so this is the same view, but now we're looking at different plates. Again, there's some small text here you don't have to worry about. But we can divide Earth up into about a dozen plates. Some quite big, like the Pacific is quite a big one. North American plate, also decent size. And so we're here in California astride these two different plates. And so these plates, these are the outermost rigid part of the Earth that are shifting around and bumping into each other, pulling apart from each other. And so the short version of plate tectonics is we have two different types of crusts. So the type of crust that we create underneath the ocean is heavier and thinner. So it's thin crust and it's heavier. And so it sits lower. If you think of like a heavier ice cube, it's going to sit a little bit lower. And so a lot of the ocean crust is underneath the oceans. Comparatively, the continental crust is lighter, a little bit less dense, and thicker. It's 2 to 3 times as thick in places, in some cases more. And so that's an important component of what happens when these different plates run into each other or pull apart from each other, which we'll get to very shortly. And then the other factor is we have 3 main types of plate movement. So we can have 2 plates that diverge from each other, so they're spreading away from each other. And that's a good place to create new crust. We can have convergent, so the 2 plates are smashing into each other. And then we can have transform where things are going sideways, like our famous San Andreas Fault example here in California. So if you add the different types of crust, ocean bumping into continent or ocean bumping into ocean, with these different variations of pulling apart or running into each other, then we get the different style of plate boundaries that we have on a global scale. And the tiny numbers that you can't see are telling you the rate that the plates are moving. These are in millimeters per year. And so it's basically from almost 0 up to 150 millimeters in extreme cases. But on average, the best way to think about it is the plates are moving at about the rate that your fingernail is growing. Okay, so that's what's driving the Earth, is these plates shifting around at that rate. And you add enough time, that adds up to big earthquakes, magnitude 7, 8, 9, at a lot of these plate boundaries where that movement has kind of been built up and then released pretty abruptly. Okay, so that takes us into what California looked like in the Mesozoic. So this is from about 250 million up to about 65 million, that period of time. So this is the period of time when we had the dinosaurs. And this is what was the plate boundary along the coast of California during that time. And I'll play it through. This is a really nice animation plate tectonic professor put together. And so what we have is we have a very thin, dense ocean plate that was running into a thick, comparatively lighter continental plate. And so when that happens, the ocean plate ends up diving underneath. As that dives underneath, a few other things are happening. So we're creating big earthquakes here. This is happening over tens of thousands of years to millions of years. What we're watching here, again, fingernails sped up in time. And so you can see there's some material that's being scraped off at this trench, this deep spot. We also were creating volcanoes. So I'll play this through one more time. There we go. So yeah, we have material that's being scraped off and added to the coast of California. At a distance away, we actually have some melting that's occurring, and that melting is going up. It's feeding these magma chambers a couple miles underneath, a few miles underneath the surface, and then that is a magma chamber that's feeding this chain of volcanoes. So this is happening all along this chain, this arc. And this is very similar to what's happening in the modern Andes, but this is basically what was happening for much of California during the Mesozoic. And so if we take that, we don't have this same plate tectonic setting anymore, but if we erode it down, that's essentially what we have today is a cross-section across California where the coast ranges are mostly made up of these very mixed up, off-scraped rocks from the ocean. That's the general Coast Range rocks. We have this low basin that's been filling up with sediments past that. So that's like the Central Valley. And then we no longer have very many volcanoes in the Sierra Nevada, but we have the roots exposed. So the granite roots are now what are exposed at the surface. So during the Mesozoic, we had subduction. That's where this plate is going underneath the continental one. We had accretion where material was being added. We were adding more California coastline real estate. And we also were erupting with this chain of volcanoes. So this is a view from an 18,000 foot peak in the Atacama Desert that I was fortunate to be able to hike up to the top of. So this is looking north on the Andes from across this active volcano crater here. And you can see this chain of volcanoes off in the distance. This area is very high elevation generally with even higher volcanoes poking up through it. This is another view looking the 180 degrees the opposite direction. And you can see some volcanoes look younger, have this better shape, and then others look a lot more eroded away. And so if you imagine, this is basically what California would have looked like during the time of the dinosaurs. Maybe a bit more vegetation, but this chain of active volcanoes. And you can imagine all these magma chambers underneath each one of these volcanoes kind of overlapping in time and space to feed these volcanoes. And so this is what Sierras look like today. And again, we have all these granite rocks that are the crystallized magma chambers that fed volcanoes that are now eroded away that would have been several miles above the position of these magma chambers. So those rocks are all gone, and we're now just looking at the roots that were feeding the volcanoes. So this is what we have in the Sierras today. If the plate tectonic shuts off the coast of the Andes in the future, the Andes could look like this many millions of years in the future where the volcanoes erode away. Okay, this is another animation I wanted to show you just to show you this transition where we went from this subduction into our more modern setting. And so this is where we had this plate going underneath the continent, we would have had chains of volcanoes. And so what I'll show you is, even though it's a cartoon, it's actually fairly accurate in terms of what happened over the last 40 million years. And so we know this from the offshore geology. We're able to basically reconstruct what happens onshore. And so you'll see a few things happen. So watch for this boundary kind of come in, and then things are going to get kind of weird here. Notice Nevada is quite skinny, so Nevada is going to double in size. There's going to be all sorts of things that kind of happen. So here I have it plane. And so we have this plate boundary that runs into another plate boundary, and so that causes a lot of complexity right here. And then we start sliding things horizontally. And you can see Nevada has managed to kind of double in size here. So I'll play that one more time. And so 40 million years ago, that's would have been just like the cartoon that I showed before this. And then when this plate boundary runs into the other plate boundary, things get a little bit more complicated. And then we start having the strike slip. The ancestral, the San Andreas Fault really kind of gets started about 20 to 25 million years ago. Quick question? Or?
Yeah. How far north does it go? BC south?
The one before, or sorry. Yeah, so this Farallon plate was quite widespread, and now we just have a couple pieces of it. So this Cocos plate here and then the Juan de Fuca plate are the last little remnants that haven't disappeared yet, was the question that was asked. Okay. Okay, so this is what our tectonics currently looks like. And so again, California, we're actually really quite diverse, where we actually have all three of the main plate boundary types at present. And so for much of our length, we have the transform sideways motion of the San Andreas Fault system. In the south, so Salton Sea and below down into Gulf of California, we actually have spreading. So the plates are actually pulling apart from each other. So that's the divergent pulling apart. And then the very northern part of the state, just like up in Oregon and Washington, we still have subduction. And so the two plates are running into each other. That's creating the Cascades, our chain of volcanoes similar to the Andes. And so, yeah, we have all three different plate types in California. And then I also just wanted to make the point that even when the plates are moving sideways, if there's bends in them, that can create mountains or open up valleys or basins. And so some of our local mountains, like the San Gabriel Mountains, are partly there because there's a bend in the San Andreas Fault system where the two sides are running into each other, and there's a little bit more compression that's happening to push the mountains up. And so at present, we have all four of those buttons on our blender that I talked about, where we still have subduction in the north, accretion in the north, we have eruption in the north, and a few other kind of random places around California. And then we also are translating or sliding things horizontally. And then I pulled this up this morning. So this is a map of all the earthquakes that happened in the last week. So we had 541 earthquakes in the last week in California and Nevada. Most of those are quite small, which is why they're tiny little dots here. But you can see that generally they're kind of predictably occurring along the San Andreas Fault area and related faults. So along our plate boundary. There was looks like a magnitude 3 that happened a couple hours ago up at this little junction area. Yeah, so there's kind of a real obvious pattern here. There's still a cluster of aftershocks that's happening from the big Ridgecrest earthquakes in 2019. And so those are still popping off in that area. Okay, so this is a very simple map of the geology of California. We have much more complex ones than this, but we're basically coloring it based on how old the rocks are and what type of rocks they are, whether they're sedimentary rocks, layers kind of piled up at the Earth's surface, metamorphic rocks that need to be buried and undergo some pressure changes, or igneous rocks, the ones that are associated with volcanoes and volcanism. And so we have some rocks that are quite old. We have some rocks that are up to 2 billion years old in California. Those are fairly rare. They don't make up a lot of area of California, but we do have some quite old rocks. And then I just wanted to make the point that the overall pattern, as I've kind of suggested, is really due to the tectonics that we had in the Mesozoic. So the greenish rocks that we have on the coast, those are all the material that was scraped off. We have the Central Valley that underneath it has even older sediments. And then we have the band of the granitic rocks, granites that are related to the volcanoes that are now long gone. And so you can kind of see there's a band here and things get chopped up by the faults, but the bands also continue down into the Riverside area down here. So that's kind of the most basic overview of the distribution of rocks, and we have quite a large diversity, including ultramafic rocks that are poisonous to very many plants because of high levels of heavy metals, chromium, and lead, and all sorts of things like that that are not the best for life. Okay, so I wanted to give a very brief overview about how we create soil and where soil comes from. Again, there's some small text here you don't have to worry about. But this is showing a cross-section from the surface down to the base underneath soil. And so soil really is a product. I'll go through all the particular things it's a product of, but it really is a product of the rock that you're starting with. So if you have solid, unweathered rock, a limestone with calcite in it is going to be very different than a granite. It's going to have different minerals, elements contained within it, going to break down differently. And then up on the top, we have an organic layer. So leaves, twigs, and all the things that are kind of breaking down from organic material. And so we have these layers in between that are our soil horizon. So the bedrock that's really kind of largely unweathered is what we call the D horizon. Above that, we have a weathered, it's mostly the bedrock, but it's been weathered. It can be very cracked and have lots of like clay minerals within it, but no real organic material. That's the C horizon. Above this, what you really kind of think of as the soil. We have the A and B horizon, so topsoil and subsoil. And then we have the litter zone, that's the forest cover of the pine needles and leaves and twigs and things like that. So how we build up soil through time, again, we kind of start with an area that just has bedrock exposed. Rainwater gets in the cracks, starts breaking down the minerals, and tree roots and plants also help with that by breaking the rock further apart and allowing groundwater to infiltrate. And so with time, we start building up more and more soil. And so we, with time, get this very distinct layered structure that almost anywhere in the world can be recognized with these discrete kind of horizons. So that's how we're building it up through time. For our purposes here, really, so again, soil, how do we create soil, and how do we get to the different types of soil that we have? It's really a function of these five major things. And so it's parent material. So it's ultimately the bedrock, the rock that it comes from. The climate is definitely important. So temperatures, rainfall, things like that. Topography is important. So it's different on slopes versus in valleys. Organisms are important. So think of the organisms, gophers and earthworms and things like that are helping to mix up and create soil. And then time. And so the amount of time that you have a soil has to develop is another important factor. And so all of our diverse types of rocks in California lead to lots of diverse soils, and our native plants have kind of adapted to those different soils. Some things are quite hardy and not so particular. Other things can be quite particular in terms of how much drainage they want, what nutrients they want, the grain size, all those sort of different factors. And so these are just some examples. So some of our native succulents can essentially grow out of a crack with essentially no soil within it, and they're just fine with that. Not very many, but some plants are adapted to very saline or alkalic soils like you might find in salt flats or mud flats. Some plants can grow just in sand with essentially no soil development, just loose, clean sand. They're able to actually grow from that substrate. We can have carbonates, so some things like limestone and marble to grow on, like some yuccas and agaves in the Mojave Desert. Ultramafic, these are these plants that have very high amount, or this is the soil and rock types that have very high amounts of iron and chromium and all these kind of heavy metals in them. And so not a lot of plants are able to grow on them. And often when they do, they're kind of like stunted little dwarf trees and things like that. So some plants are adapted to that environment and kind of can thrive where others really kind of struggle. And then this is showing the root structure of a Joshua tree that are really quite particular. If you go out and look at Joshua trees, they really like older alluvium, older kind of loose material that came out in flash floods. They don't like the young material. You won't find them on rocky slopes. They're really particular about the type of soil that they like to grow on. So all of that is a factor in the diversity that we end up with. Okay, so again, I'm a geologist. Our recent past, I'm talking about 18,000 years ago. So that's quite that's quite recent geologically speaking, but things were very different in California at that time. So 18,000 years ago, we had that's the peak of the last major ice age that we had, the last major global ice age. And so we had globally, a lot of the ocean water was actually locked up in ice on continents and ice sheets and glaciers. And so because of that, sea level was actually 400 feet lower than present. And so all this little band of green along the coast is little extra real estate that we have. So San Francisco, for example, would have been about 60 miles away from the coast at this particular time. And we had some near land bridges where a lot of the Channel Islands were actually connected and disconnected by the mainland by a very narrow channel, narrow enough that mammoths actually swam across that channel, lived on the island, got stranded there, and then became little micro person-sized mammoths instead of the ones that should be twice this tall. So some interesting things happening there. Virtually the entire Sierras was one giant glacier, as you can kind of see. We had a lot more lakes, including in the Mojave Desert. We had chains of lakes. Even in Death Valley, we had a giant lake down there. We had a lake where the Salton Sea is, that it would have been about 6 times larger than the Salton Sea is at present. So just very different, only 18,000 years ago. And one of the best records we have from this period of time and before, completely unparalleled, is the La Brea tar pits. Show of hands in the room, how many people have been at La Brea tar pits? Okay, most people, which is great to see. So really amazing place, downtown Los Angeles today, but it's been a persistent seep of tar and petroleum coming out of rocks for the last 50,000 years. And within that, there's a unparalleled record of fossils, both animals and plants. And at the moment, they have apparently over 3.5 million different fossil specimens that they're and counting that they have at this one location. And so it's well known for all the really kind of dramatic, exciting ice age animals that are now many extinct, or otherwise you might expect to see more. It's basically more of an African safari type thing that we had here in Southern California, with a lot of very large megafauna. So things like mastodons, mammoths, tapirs, camels, horses, ground sloths, saber-toothed cats, dire wolves, bison, pronghorn, grizzly bears, we all had. In the tar pits, they also have found a huge variety of bird species, lizards, snakes, salamanders, toads, tree frogs, freshwater clams, snails, fish, and then a huge number of beetles, flies, ants, crickets, millipedes, spiders, and scorpions. And so between the animals and the plants, it's a really amazing ecosystem that we're able to reconstruct in terms of what was there and how things were interacting with each other. And so on the plant side of things, they found 158 species of plants within the La Brea tar pits, so over the last 50,000 years. And this comes as fragments of wood, twigs, seeds, cones, leaves, pollen. So all those sort of different things we're able to, are the fossils that are being preserved. And overall, those show that over much of this period of time, 50,000 years, especially going back 50,000 years. Downtown Los Angeles, it was a much wetter and cooler climate than present. And so think of Big Sur as kind of more what the climate was, like foggy, coastal, claggy kind of conditions. And so these are the four main kind of ecosystems that they've been able to reconstruct from the species that they see. So there was still coastal sage scrub at this time, as well as chaparral and riparian corridors along rivers. But we also had mixed evergreen and redwood forest pretty close to downtown Los Angeles. And if you go there, I think it's a fairly new thing, but they have a Pleistocene garden that they've created where they actually have all the plants, or a number of the plants that they found as fossils from 50,000 years ago that you can see there in the garden. So kind of a unique approach on a botanic garden. Okay, so now we're going to slide through some demographics talking about the state overall. And so, as you probably know, we have really amazing diversity of topography in the state. We have the lowest point in the Western Hemisphere, and that's Badwater in Death Valley. That's 282 feet below sea level. And less than 100 miles away from that, we have the highest point in the lower 48 states, which is Mount Whitney at 14,505 feet. So really huge, dramatic changes in elevation across the state. Associated with that, we also have some very steep slopes. And so San Gabriel Mountains and San Gorgonio and San Jacinto are kind of some particularly steep areas that we have in Southern California, the east side of the Sierra Nevada as well. So that's one important factor. And then I wanted to introduce, probably for a number of you, this new concept of a geomorphic province. And so essentially what this is doing, if we look at this map of California, again, it's just colored by elevation to show the different terrain here. And if I gave this map to a 10-year-old and said, "What can you separate out some areas based on their texture, their properties, their elevation?" they'd probably come up with a somewhat similar, but maybe not quite as detailed map as this. And so these are California's geomorphic provinces, and these are geologic regions that display a distinct landscape or landform. And so elevation, rock types, is it all kind of a volcano area? Is it a low elevation area? Is it mountain ranges? That's how we divide up California as geologists in terms of the landscape and the landforms. So that's here. And hopefully you can kind of see some of the logic that maybe is in there, maybe some of the nuances a little bit lost on some of us here, but overall that's how we get to these 11 geomorphic provinces. So climate, we also have 11 climate zones in the state of California, which is again quite a diversity. And so this is a function of the precipitation, the temperatures. So latitude has a little bit of a factor where we have a decent latitude range from the top of the state to the bottom of the state. But quite a lot of this has to do with being along the coast. We have moisture that comes in off of the coast. We're having some now. And then we have a number of mountain ranges that form rain shadows, where most of the rain falls on mountains, and then you have comparatively less past that. And so you can see that very nicely in this precipitation map, where we have a quite dry Mojave, Colorado desert over here. Also, the southern part of the Central Valley is a rain shadow behind the coast ranges here in Big Sur. So the precipitation, that leads us to these different climate zones. Again, plants very much are adapted to particular climate zones within potentially a range of 1 to 2 of these. And so this is, again, the topography is controlling the precipitation and the local climate to some extent. That, again, is going to control our distribution of plants. And so here we go. So now we get to finally talk about biodiversity. So according to this one compilation that is pretty widely cited, that looked at all 50 states, California ranks #1 in terms of biodiversity, so plants and animals, biodiversity generally, and also #1 in terms of endemism. So we have more plants or more species found here than that are adapted to here than anywhere else, only found here than anywhere else. We're also pretty high on the list for risk and number of extinctions that have already happened. So even though we have this amazing biodiversity, we actually lost a lot of biodiversity as well. As you well know, we're home to some of the tallest, largest, and oldest living things. And again, we have 11 vegetation zones. Hopefully you can look at this map of the vegetation zones and see there's a lot of similarities to the geomorphology map that I showed you before. We're breaking things up a little bit differently, like the Sierras are now broken up a little bit differently by latitude. Same thing with the coast ranges, but the general pattern of these vegetation zones, CalVeg vegetation zones, are still very similar. Okay, and population. So it's also worth having a quick look at. So population, if we look at modern population of California, in simplest terms, the high population centers are coastal ports and kind of evolved from the coastal ports into whatever else they do. But we have San Francisco, Los Angeles, and San Diego. So we've got three major coastal ports. They're these major population centers. And then we have a discontinuous band inland that are really kind of supporting agriculture, right? Those are our main growing areas out in the Coachella Valley, and then up through the Central Valley as well. So that's really kind of what's controlling our modern population, is really those two factors. I think quite interestingly, and again, I apologize that its text is completely illegible, but in all of North America, California has always been home to more numbers of different native people and cultures than any other region or state. And so this is one representation. Obviously, there's kind of overlap between these different groups, but it gives you some sense of just how diverse the native peoples of California are. You can see some of the size of some of their ranges that definitely would be a function of their culture and their natural resources that are available to them. Are they foraging over a large area, or do they have one kind of estuary or river mouth that they're really kind of focused on? And so again, I could make the argument that to some extent the distribution of peoples and their kind of way of living and their culture is a function of the natural resources that were available to them, food, shelter, that were available. It all comes down to the geology. It's what my thesis is here. And so here we are looking at all these together. So this is a map of all the active faults in California. You can see it has a lot to do with the topography that we looked at, the map of the different rock types that we looked at. And then again, just kind of highlighting just how similar the geomorphic map we have is to the vegetation map is. So there's a lot of relation here that has to do with the rock types that are present, the topography, and some of the local effects of precipitation and things like that have to do with the topography. Okay, and last thing on California, just another point of pride for us as a state is we have more national parks than any other state. So we have 9. So we've got these 8, and then of course our local Joshua Tree National Park. And again, just to kind of make the point that biodiversity is a very important part of these national parks, as well as the geology, as you can see, kind of nicely featured in these posters. Okay, so with that, I'm going to shift, and we're going to talk about one example out in the Mojave Desert that I think, or out towards Palm Springs in the Coachella Valley, that I think is a really interesting example of geology and vegetation relating to each other. And so other than the very non-native golf courses and things that we have down here, hopefully you can kind of see there's a little band of darker things kind of up here in the Indio Hills just north of Palm Springs. And so here I've highlighted these dots. So these are little pieces of vegetation. You connect the dots and you get the San Andreas Fault. And so what these are California fan palm oases. Each one of these little dots that I highlighted here that are sprinkled along the San Andreas Fault. And so essentially what happens is the San Andreas Fault has a layer of basically impermeable material like clay right at the fault. And so what happens is the groundwater that's coming through the shallow subsurface is coming off of the mountains. It runs into that barrier and is basically forced up to the surface. And so in this environment that usually is very dry, plenty of sun, but not a lot of water available for plants, you all of a sudden are able to have these palm tree oases and other plant species that are kind of supported by the shelter that they give. And how many people here have been to Thousand Palms Oasis? Okay, so fewer people. That I definitely recommend. It's a preserve that's open to the public. You can look up what their hours are. I think it's just daylight hours most days. That's at this location here. Here's the parking lot. It's a really neat oasis to walk through. There's palm trees and boardwalks and a pool. But you could also hike up to the top of this little hill here and see this really dramatic line that is the San Andreas Fault. So you can actually see it because of the vegetation. There's no step in the landscape there. It's just because of the vegetation that's growing on the upstream side because the water is coming in and then ponding against the fault here. It's a really neat kind of example. Definitely recommend it. Thousand Palms Oasis. Okay, and this is my only slide that really has nothing remotely to do with plants, but it should be a point of pride for us here in Riverside, but nobody knows about it. So this is a world famous location that basically no one knows. It's just a hill hidden behind the city dump. So this is a little hill that was mined during the 1940s, operated until like 1986. And all they were doing was just mining the marble for cement. And so it was limestone that was baked by granite, and whatever the conditions were, it created a lot of really unique and weird minerals. There's a mineral called riversideite that's first described at this location. There's quite pretty blue calcite, and this is that Vesuvianite mineral. But I make this point that there's only one other place in the entire world where more species of minerals have been found in one location than this spot, and nobody knows about it. It's just a place behind the dump. You cannot access it at the moment. You can get a little bit close and look through chain link fence. Here, I'll show you. So here's our kind of aerial view looking over downtown Riverside here. So now I'm going to shift to talking about Riverside for the last few minutes of my talk. And so here we are in downtown Riverside. Those that are physically present, we're kind of right here at the base of Mount Rubidoux. Here's the quarry that I just mentioned right next to the city dump here. And so the last few slides, I just wanted to highlight some of the vegetation that changes that have happened in the Box Springs, which is something that I've been compiling. So these are highlighting the major open spaces that we have around downtown Riverside. And so what I'm going to do is I'm going to start with a historic photo from Mount Rubidoux looking to Box Springs. And so this is this view. And so we're physically located just a little bit to the right at the base of the mountain off the side here. But this is a view from Mount Rubidoux looking to the Box Springs in 1890. So looks a bit different, a lot more orange groves, definitely no UCR over there. But yeah, you can see that this is what the vegetation was at the time. So we had chaparral on the top and then coastal sage scrub on the lower slopes. And so this is information I compiled from Rich Minnick, who's a fire ecologist at UCR, and did a number of these different maps to see how things have changed over time. So 1929 is the oldest aerial photos that we have. And from that, you can see, again, very similar to 1890, we had chaparral on the high parts, mostly on the high parts of the hills here, the mountain range, with coastal sage scrub dominating all the lower slopes. If you look at aerial photos from 1952, things are starting to change a bit. And so the yellow that's being added here is grassland. So this is invasive Brome's grassland that's being added here at the expense of some of the natives. And if we zoom to 1995, things are basically completely inverted, where the grasses have completely taken over a lot of places within the Box Springs. And so all the yellow here is these invasive grasses. These are the key species. You guys are more experts than I am, but coastal sage scrub, things like brittle and then we've got chaparral, things like chamise as well. And then these are the two major bromes that are invading in the Box Springs, basically taking over red brome and ripcut brome. Okay, last slide about this. So this is more data that Rich Minnick compiled, showing a number of different things, looking at fire history, how the abundance of native plants and grassland has kind of changed through time. I'll go through this very quickly, but just to say, like, we're looking at 1920 up until like 1995, and there's big changes that happen in the 1960s, basically. So we start greatly increasing the invasive plants at the expense of decreasing the chaparral and the sage scrub. And you can see there's a pretty significant step decrease in the amount of chaparral that's present. And so Rich's quick take on this is that we had a series of very heavy rain years in 1965, 1966, and 1969 that really allowed those grasses to proliferate. They really just kind of took over that short period of time. And that was combined with decades of unusually short fire intervals. So typical fire interval for a particular location in the Box Springs should be more like 25 years, but it was going down to 5 or 10 years in a lot of places. So both of those contribute to this really rapid conversion into grasslands. Okay, so a couple slides and we'll wrap up here. If people wanted to take a local field trip, this is, I think, an interesting example showing the effects of aspects of what direction a slope is facing on vegetation. And so there's a trailhead here that kind of goes up this ridge, goes along this ridge. And at this location, there's a really nice dramatic example where all the slopes that face south, so this slope up here, you can see it looks a little bit more desolate maybe, and this slope here are both south-facing slopes. Those do a pretty good job, probably because of the amount of sun that they receive, of still having sage scrub, native cacti, and they have naturally very thin soils. So those areas are a little bit more resistant to this grassland conversion because they're just getting absolutely blasted by the sun. And that's in contrast to north-facing slopes. So if you go to this area and look at the north-facing slope, that's basically all grassland. There's very thick soil. You'll see gopher holes everywhere on the north-facing slopes, but almost nowhere on the south-facing slopes. So it's kind of a real nice example. You can go out and see, and it's really kind of clear to see that effect of the direction that the slope is facing as a function of the vegetation. And then my last slide on the Box Springs, I just wanted to show one area. This is also near that Two Trees trail that I just highlighted, just to show the biggest threat to the native plants and the ecosystem that we have in the Box Springs. So this is one area that we're looking in 2018, and this is the same area 5 years later. So there's some pretty big differences between these two images. And so it's these cute little twerps. So yeah, we've had a huge explosion of the donkey population in the Box Springs. They're creating trails all over the place. They definitely like the grasses, but I've also seen them eating and trampling the native vegetation. And you can see the density of the trails are essentially right next to each other in terms of how dense they are. And so this is eroding the soil, creating erosion issues, and also taking out the vegetation. And so just to highlight that this is the biggest threat that we have, not fires, not really invasive plants so much as it's really the donkeys that are doing the most damage at the moment for this preserve that we have. Okay, and so with that, I'm going to end with my very quick summary here and really just, again, finish by making this argument that geodiversity is really what gives you biodiversity. And so tectonics, the unique tectonic history we have that's led to all the different rock types, that leads to all the different types of soil. That tectonics gives us the different topography we have with valleys and large mountains and volcanoes. And then it also gives us, to some extent, the climate. So all of those factors, that amazing diversity of geology that we have is what really leads to our very high biodiversity that we have as a state. And then again, just to sneak in this perspective, if you think like a geologist, we could actually call some tropical and subtropical plants California natives. Not so much anymore, but over the last 80 million years. And then I just wanted to end that if you found this interesting, I was just going to highlight a couple books. So there's a book called Assembling California, written by John McPhee, very excellent writer that's kind of more of a narrative following geologists around the state talking about different aspects. And so it's a very easy to read narrative book. And then California's Amazing Geology is a really nice kind of more textbook style if you want something on your bookshelf to kind of reference different aspects of geology. So with that, thank you very much for your time, and I'm happy to take questions.
Great. Thanks very much, Nick, for that really super presentation. I've lived in the area for many years, and it's great to have a better understanding of the interplay. And your graphics of the plate tectonics were amazing. Thank you. It really helps understand it.
Good.
So let's see. We've got some questions in the Q&A. First question is from Merritt. It says, I live on Mount San Jacinto. When and why did this mountain uplift in geologic time?
Okay, so the question for the room is someone lives on Mount San Jacinto. When and why did that mountain uplift? I'll mention that I think in terms of a lot of places in California, there's a lot that we don't understand about Mount San Jacinto. It is very unusual just how steep the north slopes are. If you drive over the pass there, it's really quite unusual. The kind of short, simple version I can give you is that it has to do with the different branches of the San Andreas. So we had the San Jacinto, it basically is coming up between the San Jacinto Fault and see if I can find a map really quick. I don't have a great close-up. But San Jacinto is coming up between the San Jacinto Mountain is coming up between the San Jacinto Fault, which is here, and then the San Andreas Fault. And so it's really kind of the history of those two faults that have brought up the mountain. They're also very unusual for California, very resistant, hard, unfractured rocks. If you go up the tram, you see those big, giant vertical cliffs. And so that's part of the reason is they're not eroding as fast as some other places, but also because of its position between these two major active faults. And so the time frame for that, it's probably the last 5 million years or so is kind of the history of that mountain range coming up.
Great. The next question is from Susan, and she asks, speaking about the donkeys and the problem they cause, what is the solution?
Okay, thinking about the donkeys and the problems they cause, what is the solution? We need to get rid of them. I think they need to go somewhere else. The population is just, you can kind of see that it's not really, the landscape isn't really able to sustain or support the number that we have. The one benefit I would say is that they do reduce the fuel for fires. So that's probably working against us trying to get rid of them. But yeah, we just clearly have too many of them, and they're just creating trails all over the place. And yeah, there's complications where they're a federally protected species, state protected. Okay, yeah. So I present it because I think it's a major issue as a from my geology perspective, as well as what I've seen with the plants. And so I'm hoping someone has an answer to that question that's better than mine. But yeah, I think really it's just not sustainable at the moment what we have.
Well, they quite double their population 5 years, right?
So for those online, there's a comment that equines can double their population in 5 years. Just
But I've heard it treat the meat right and tastes just like chicken.
okay. Any other questions?
I just
Yeah.
wanted to mention that
Oh, there's actually some more questions on Zoom.
Go for it.
Susan asked, what is the change in climate from 50,000 years ago attributed to?
So it's really kind of global variations in climate. And so we have these global cycles that happen, over the last several million years. We have these global cycles that are kind of about every 50 to 100,000 years. We have like a major full shift in the climate. And so in the crudest sense, these big changes that we're talking about have to do with the Earth relative to the sun and how the Earth is positioned. So we have a little bit more of a tilt sometimes. Sometimes we have a little bit more of a wobble. Sometimes we're a little farther away from the sun. Sometimes we're a little closer. So all those little kind of adjustments actually have a bulk like climate signal that actually change our global climate. And so in the crudest sense, those are the biggest factors. But then other things like, life and how they change the atmosphere and the greenhouse gases that are present. That's also a factor that we're obviously seeing at present. But the biggest bulk factor when you're looking over these millions of years, the last several millions of years, it's all the little adjustments in how much the Earth is wobbling or tilted or distance from the sun. Yeah.
About the speed.
Great. So there's actually a couple more
I
questions
think
in the
speed is
chat.
fairly constant. Yeah, I think
Oh,
speed's
sorry.
not. Go ahead.
Couple more questions in the chat. The next one is, can you suggest a good geology book for our area, meaning Riverside, Idlewild, Coachella Valley?
So the one I highlighted does have some good overviews of so California's amazing geology that will kind of include, that's a statewide, but there is some good discussion of kind of Southern California, our kind of general area. Another one I would recommend is there's a roadside geology guide to Southern California. The author on that is Sylvester. And that's quite a good book too. It's has some road guides that you can follow to go actually see some of the different places. And yeah, it does a nice job highlighting particularly some of the geology areas out in the Coachella Valley area. I think they do a good job highlighting. Yeah, I'll type it in the chat, I guess. So roadside guide to something like that. You'll find it if you Google it. So that guide to
One more question from Cindy. Can you explain how the plates can be both transverse and spreading in the southern part of the Salton Sea?
Yeah, that's a really good question that you picked up on there. Sorry, let me go find it eventually. Yeah, so I think the question was kind of this area. So yeah, so what we have is a transition where we're going completely transformed, so the sideways motion. And then at the southern end of the Salton Sea, we start getting into this area where things are actually overall pulling apart. And so you can see in the Gulf of California, what we have is in red, these are areas that are being pulled apart. And then they're linked by these like sideways moving faults as well. And so this is a really common thing that we see in areas that are spreading is, if you're pulling things apart on a sphere, you actually need little horizontal faults to be able to like not open up a big gaping hole. And so if I go back to this
Nick, I'm
map,
sorry. We actually went off your screen share. So if you,
oh, okay.
I think it may be showing on there, but if you can go back to share again, please. Sorry, I think that's my fault.
It says I'm sharing. Are you seeing it or? Okay, it says I'm sharing, so I'll re-enter it, I suppose. Stop sharing. I think people said they can see it. Okay.
There it goes. Okay, sorry, I wasn't. It's coming up now.
You'll be able to put the citation to Sylvester.
Okay, perfect. Yeah, someone dropped a link. That's great. Oh, right. So what I was saying here is that, in the middle of the, let's say, Atlantic Ocean over here, overall, the two plates are moving apart from each other. But again, because this is actually on a sphere and we're kind of unwrapping it, all these little like jogs and you probably can't see my cursor here. Sorry. There we go. Sorry. So yeah, I was highlighting this area over here. And so even though this area overall is pulling apart, there's all these little steps and jogs. And so each one of those little jogs is actually moving sideways to be able to accommodate that overall extension motion. And so to some extent, that's what we have in the Gulf of California. And then, yeah, right about at the southern end of the Salton Sea is where we have that transition from the San Andreas into the first area that's being pulled apart. Other questions?
Okay, I do have a couple more questions from the chat. Sorry. So the next one is from Paul. Why are there few, if any, plants growing in the San Andreas fault gouge in the Mecca Hills? Also, I've seen a lot of clearish crystalline objects washed out of the fault gouge in the western part of Mecca Hills. It's common in some places as veins. It looks like flat, planar pieces and also more chunky pieces. It barely reacts to acid, so I don't think it's calcite. Could it be selenite?
That's what it is, yes. Yeah, so the question for those here, we're asking about the Mecca Hills, this area in the Coachella Valley, kind of a little bit north of the Salton Sea. So yeah, it's a very desolate area for vegetation, and it's really largely a function of the rocks there. There's a lot of rocks that are very muddy. They're not well drained, and yeah, I think things just have a hard time growing there, other than, again, the washes. You'll see plenty of plants. So I think overall, when you're looking at the hills there, it's kind of more badlands. And a lot of that is probably directly a result of the rocks, and particularly being particularly muddy, and not well draining and not having a lot of water. And then yeah, the kind of window glass clear crystals you're talking about are selenite, also known as gypsum. And so yeah, those are growing in the veins as you mentioned.
Okay. That's all the questions in the Q&A. There's a couple in the chat, but maybe if you want to go ahead with the questions in the room, and then I'll skim through and find what's remaining in the chat.
Questions in the room?
I just wanted to mention that more than 60 people followed this to the end on
Okay.
Zoom. And the kudos that are in the chat are pretty amazing.
Oh, great.
Including somebody that wants to know where they pull cord. UC Riverside.
Yeah. Thanks. So yeah, Arlie was just mentioning the comments in the chat that I haven't seen. So thank you for those comments. I'm glad it was enjoyed. We do occasionally teach a California geology class, but yeah, a lot of this is kind of the intro class I teach. I usually try and put a little bit of California geology in so people can understand their backyard.
Somebody else mentioned another book, Lands in Motion and Geology of Joshua Tree.
Okay.
As being an outstanding book.
Great. So, and that's mentioned in the chat.
It's in the chat.
Okay. Yeah.
Okay, I'll let other people ask questions.
Questions? Yeah.
I want to talk about the San Andreas Fault for a minute. We used to live in the San Gabriel Mountains in a town called Wrightwood.
Oh yeah.
And we were told at the time, this is a number of decades ago, that the San Andreas Fault runs right through Wrightwood. At one time there was a private country club, small little country club that had tennis courts, and they resurfaced the tennis courts with asphalt. And then a few years later, cracks started showing up. And I wonder, when you pointed out how slowly plate tectonics moves, I'm wondering if that in fact was the cause of what was happening, or maybe it was a root from a plant, from a tree or something like that. But is there anything noticeable in nature where you can see changes like that?
Okay, so the question for those of you guys online was about in Wrightwood on the backside of the San Gabriel Mountains. It sits right on top of the San Andreas Fault, and there was a observation that there was a new tennis court that went in across that area and then started deforming and cracking and breaking up. And so the question was, is that indicating, the motion I mentioned as far as plate tectonics, is that potentially the explanation? And so this is a little more nuanced, but so when I'm talking about this plate tectonic motion of the, moving at the rate of my thumbnails, think of it as mostly like it's building up at that rate and then releasing in earthquakes is usually what happens. And so most of the kind of plate boundary motion that we're talking about, it's that fingernail growing, and I like to do kind of like you push your two hands together and then try and slide one past the other, and you can kind of feel that there's the skin and the friction is kind of holding it in place, and then at a certain point it gets enough that it actually slides and lets go. And that's essentially what's happening, is we're kind of building up this strain until it reaches its breaking point, and then we have a big earthquake. So that's the most common scenario we have. There are places like Central California on the San Andreas Fault that instead of having big earthquakes, it has such low friction. There's actually serpentine and other minerals in there that just are like super lubed. And so the fault actually does just creep continuously. And so a really great place to see this, or you can look up online the town of Hollister. If you type in Hollister creeping fault, there's entire neighborhoods that they're everything, their houses, their walls, their curbs along the street, you can see them deformed. And so it's a real classic place that geologists like to go out, or take a geology field trip. And particularly they're not doing it as often as they used to, but they used to stamp the year of the concrete when they put in like sidewalks. And so it's great where you can actually measure, okay, this was 1967, and you can measure how much movement has happened. So that's an unusual case. But Central California, we know that part creeps. We don't know of any creep in Wrightwood. We know there's big evidence for big earthquakes in Wrightwood. So most likely it's probably like just the ground settling differentially. You can have different rock types on both sides of the faults that maybe settle a little bit differently. So it's probably in that case not tectonic motion that you observed. It's just kind of the foundation being kind of more unstable. But yeah, good question, and a real interesting kind of situation where things actually can creep in some places.
Speaking of Brightwood, I was up there once with a class, looking at the San Andreas Fault, and we're near Brightwood, stopped, and the instructors said, look at that ridge up there. It was like the North Ridge, I think, on Brightwood, and how flat those trees are, those pines are, those conifers. And he said, and it was, kind of flat. I mean, he never noticed. He goes, well, that was from an earthquake. And he checked me on this, but it's a walls plant. So he said it snaps the force of the quake was so sharp, it snapped off all the trees on this ridge line. Have you heard of that?
Okay, yeah. So for those online, the question was still talking about Wrightwood, and they visited the Wrightwood area and on a field trip, and it was mentioned that there was a ridge of trees that snapped in a San Andreas Fault earthquake. So yeah, that is something that happens. I don't know about the specific example that you're talking about, but yeah, we actually use that to work out past earthquakes. And so what we can do is we can look at trees and core them. So you core a tree, nice thin little, take a core through nice, ideally old trees. So you get a nice long record that's several hundred years. And you can core trees that are right on the fault that would either have their tops, broken off, or they could have their roots directly like offset and broken. And so those trees get really stressed out. And then you look at trees that are at a distance away from the fault, and then you see that those trees are just fine. And so you're able to kind of unravel the climate effects and basically say, like, this is evidence for a big earthquake that ruptured the surface and damaged these trees. And so yeah, that is an important tool that we have where the trees are able to kind of give us some ages of past earthquakes.
There are more questions that showed up.
Okay,
You're welcome to-
I'm willing, yeah.
Um, so, one of them was, will the Sea of Cortez join the Salton Sea Fund?
Okay, so the question was, will the Sea of Cortez join the Salton Sea at some point? So at times in the past, it has. So there's marine sediments that go all the way up through the Coachella Valley, pretty close to San Gorgonio Pass. We're kind of near Cabazon and that whole area. And those are, I don't quote me on it, but I want to say like 5 million years ago or so. So there's been periods of time in the past where it has definitely extended all the way up there. And really largely what we have right now is we have the Colorado River drainage system, big multi-state river system that's coming down, coming through the Grand Canyon. And then it basically has a fan delta that, depending on where it's spitting out, it can either the Colorado River either flows into the Sea of Cortez, or it takes a right, which is a left turn, or it takes a right turn and goes into the Salton Sea. So it's really that pile of sediment that's separating the two. But yeah, as you know, the Salton Sea is the Salton Trough is below sea level. So yes, it absolutely would like to be a part of the Sea of Cortez. It just has this pile of sediment that's kind of acting as a dam, and currently the Colorado River is going into the Sea of Cortez instead of into the Salton Sea. So the ancient lake, the real natural lake, is called Lake Cahuilla, if you've heard of that. There's a modern Lake Cahuilla there as well, but the ancient Lake Cahuilla is the one that was 6 times bigger and covered the whole Salton Basin, basically.
There's another question.
Okay.
It has to do with clay.
Okay.
So, Janet would ask, if you could, wait, there. So how clay soils tend to form in this area? What's the geologic origin of these to the clay area?
Okay, so the question was, what's the geologic origin of clay soils? And so yeah, clay, it's very fine grained. And so usually you're settling it out of lakes or oceans, basically. So an ocean basin that's very calm. So maybe like the middle of like the Santa Barbara Channel is an example where you have very fine material that's settling out. Or in the major lake basin. So if you think of again, around the Salton Sea, that ancestral lake that was there, the dry lakes out in the Mojave Desert, those areas here. And then if we go back millions of years and turn those kind of sediments into rocks, they're also going to be very clay rich as well. So yeah, generally most of the clay soils have to do with these rock types that are either muddy marine rocks or lake deposits, essentially. And so a lot of the badlands that we have in California and like Badlands National Park and places like that, they're either lake sediments or marine sediments is the most common.
I think that's it. Yeah. Gosh, thank you so much.
Thank you, everybody.
Nick, there was a couple more questions. Are you still there?
I'm still here, yeah.
Sorry, this is Katie. There's a couple more questions that came in through the chat, and those have to do with several people saying they'd like to take.
Your students ask questions. This is great.
Several people who'd like to take a semester course on your topic, and they're asking if where they can take your class.
I'm at UC Riverside, so you could look up scheduled classes. I think it's maybe a little tricky to sign up for classes if you're not a student, but you could kind of certainly look into that possibility. I sometimes teach an intro geology class, Geo 1, and that often has some more on the basics that I covered, as well as a little bit on California geology. And then we're going to try and more reliably teach a course that's specific for California geology. And people here may also be interested. There's a class that's specifically on California vegetation that's commonly run as well, and would probably be a good class. Yeah.
Great, and lots of very positive comments, and thank you very much for the presentation. Everybody loved it. And I just want to remind folks that these presentations are recorded, and there's a couple places in the chat where we've posted the link to where you can find it on YouTube. It usually takes a few days, so maybe look for it middle of the week. But we do post all of our presentations. And thanks again. That was really great. And I know everybody was thrilled, and some real geology nuts as well. Thank you.
Great. Thank you, everybody.